Okay, let's get going. So, today is going to be all about antibodies. So, last class or last video, we talked about making sure we have a fully functioning B cell. The main goal of creating a fully functional B cell is for them to shed those B cell receptors, which become antibodies. So, what's the point of these? What do the different types do? Let's get into it. So first off, how they look, how they are composed. So what is the architecture? Well, we have two heavy chains and two light chains. So let's look at that. In the yellow is the heavy chain. The heavy chain. In the red, or the pink, is the light chain. The light chain. And these are connected by some disulfide bonds. That disulfide just means two sulfur atoms. Then we can subdivide this into the Fab region and the FC region. The Fab is the top of the Y, so right up here. And the FC is the stalk, the stump of the Y. So what's really important here, though, is the variable segment. So at the end of the Fab region, at the end of this upper segment, I've changed the hue slightly. This region here and this region here, that is the variable region. The variable region. So this is really, really crucial for antigen binding. All right, so that's where it happens. So you're like, well, why would I want to change the region that is encoding for the handshake, that's encoding for me tagging pathogens? Well, this is how we get the wide variety that we do. This is how we do somatic hypermutation. We mess with this region here, as much as we can until we get the best fit possible, the highest affinity possible. So we play Wheel of Fortune with the DNA that makes up my variable light chain and my variable heavy. Down here, so this is constant light chain, constant heavy, and all of this is constant heavy. You can have 3 sections or 4 sections depending on the antibody. I'm not concerned with that though, just to be nitpicky. So yeah, I went over that. Terminal region, that's where antigen binding occurs. It's crucial that that's functioning properly. And remember, just a reminder for affinity maturation, right? We want that variable segment to be as adept as possible. So this is what affinity maturation is working towards. And that's that somatic hypermutation, and then the competition for survival skills. Or I keep saying that, for survival signals. So we make the best receptor possible, and then the best of the best compete. So it's kind of like med school. You know, you go through all of these hoops and hurdles only to then be surrounded by everybody else that went through hoops and hurdles. So really cool process for selecting the best. The first antibody we're going to talk about is IgM. IgM. This guy's a cool character because it always forms a pentamer in serum. So use your context clues. Pentagon, 5. We're going to form a 5-sided chain of antibodies here. I don't know the biochemistry, so I'm not going to make you know it, but for whatever reason, it likes to do this in serum, in our blood. It's about 5 to 10% of the antibodies. Not necessarily the highest affinity, so not the best at tagging, but high avidity. High avidity. Cool concept I want you to understand. So affinity, we talked about, is how much you like something. It's how much these molecules are ready and willing to bind to something. So it's that 1-to-1 strength. Avidity is the net strength. So maybe it's not that strong, but if it has 10 arms, well, then it's going to have some advantages over you. So avidity is more so the net strength. So with something that's a pentamer that has 10 binding sites, well, I have more potential to tag things. I have more potential to bind. It could be way less effective, way less strong, but because I have 10 sites, there's a higher avidity, a higher net strength. All right. Function, it's an excellent early neutralizer. Really great at activating the complement system because of that high avidity. So IgM, one of these IgM pentagons is enough to get the complement system going, where you need more IgG to do the same. So because of that high avidity, we can get it done in one shot go. It's the first antibody secreted before affinity maturation. All right, so what that means, again, excellent at early neutralization. But that means that I didn't have to do any messing with for this to be here. So IgM is a weird one. IgM is the first antibody, or the first B cell receptor, that's expressed on B cells. Natively expressed, just hanging out. Most of the time, we're going to edit this and change IgM, but it's cool to know that this is the first one. So there are conditions, if you really want to impress an immunologist or a infectious disease or anybody in pathology, there is something called I think a CD40 ligand deficiency. This is one of the signals that tells your B cells to switch into one of my other antibodies. If you don't have this, then in serum, all we see is IgM. So that's pretty cool. That's a good way to know, or that's one of the smoking guns, how we found out that IgM is one of the is natively expressed on B cells, because if we don't have this factor, if we don't have this signaling, then we don't get any other types of antibodies produced. So then we're really, really bad at opsonizing bacteria because I don't have IgG. We have terrible mucosal defense because I don't have IgA. So this is a cool case study you can look more into if you're interested. Okay. Next up is IgD. I don't give a dang about IgD. Boring as heck. Don't really know maybe not boring isn't the right word. Maybe we're ignorant. I don't have a lot of information on it. Any information I find is 1 foot in, 1 foot out. So just know that it is very low count, and that it is technically also natively expressed on B cells. But because of how low content and how much we don't understand the function of it yet, I'm really more so concerned with IgM being the first, the natively expressed. But technically, IgD is too. Now we get into the star player, right? This is the MVP of our antibodies. IgG, the most prevalent antibody in our system. It is running around as a monomer, so just one, mono. Excellent opsonizer. Remember, opsonizing, fancy word for tagging. It's fine for the macrophages to eat with their hands. It's kind of gross, but if you just eat with your hands, that's a quick way. But if you have silverware, well, it's much more efficient. Okay, so that's another good analogy for this opsonizing. The antibodies are our silverware. Allows for the crossing of placenta IgG, so this is a rarity we'll talk about. It's the only one that does that. Has a long half-life, so IgG has properties that if it's ingested by one of our cells, well, we just pop it back out and throw it back into circulation. So it exists for quite a while. And it's the main isotope in secondary immune responses. And if we know anything about those, right, that memory response hiked up, a pathogen wants to try us again, well, now I have really efficient IgG at the ready to say, please go away. Again, best opsonizer possible. So antibody-coated pathogens get tethered to those phagocytes. Oh, I was ahead of myself. I didn't even know. Kind of like silverware. So I'm tagging that, slowing the pathogens down. My phagocytes are just like, oh, this is much easier to get rid of. I have a fork and a knife. Let's get at it. So IgG is great for that defense. IgA, we talked about this a little bit last block. This is the antibody associated with your mucosal defense. A monomer in serum, but a dimer in mucosal secretions. 10 to 15% of my antibodies, so pretty good chunk of them. And the dimer refers to the fact that we kind of bind the ends together and have a doublet. If you recall from last unit, they prevent pathogen attachment to mucosal surface, and they neutralize without inflammation. So the whole goal is that hopefully I find a pathogen that's trying to climb up one of my mucosal trees, be it respiratory, urinary, or GI, what have you. I find the problem there, and then I can bind and dispatch it there. If it's in serum, it's fine. We have defenses in place for that, but then that's more of a diluted issue or dispersed issue, rather. If I can isolate it where I'm tagging it, well, then there's less inflammation. So that's the idea behind this, neutralization without inflammation. We get it in the region that it is existing in, rather than in the serum that's more dispersed. So yes. GI, respiratory, and breast milk. All right. And last but not least, definitely very, very piddling in percentage. We do not have a lot of these, but you should understand them for allergies. If you guys get deeper into pathology and immunology and allergies, this is very important. So they trigger the degranulation of those basophils and mast cells. Really good at a swarm defense against parasites, but a real major role in allergies. Like if you've heard of like anaphylactic shock or just these hyper heavy allergic responses, they are typically IgE mediated. IgE mediated. And the fancy word for allergies is hypersensitivity. Okay, so that's where these come into play here. We're not talking about allergies too much. I believe that's Unit 4. We'll go deeper into that. But so very low percentage, but you have some that are just ready to go, already bound to mast cells. And once that response is initiated, well, it has a really compounding and cascading effect, thanks to this body here. Okay. So I've already hinted at this. We start with IgM, maybe a little bit of IgD, and then we have to class switch into our other friends. So, class switching, the process by which B cells change the constant region of their heavy chain. So let's go back really quick. So I'm changing this right here. I'm messing with the DNA that makes this up. And this chunk here is what imparts the class of the antibody. Okay, so if I change that, right, I'm not changing the antigen binding site at all. That's all the way up here. But what I am changing is what type of antibody I am. and it's going to be one of the ones we discussed here. So IgM, IgD to either IgG, IgA, or IgE. Remember, these guys are really tiny in quantity. So most of the time we're talking about IgM into IgG or IgA. Okay. So we accomplish this while maintaining the specificity. Like I said, the antigen binding site is left alone. And it occurs in the germinal centers of those secondary lymphatic organs. So in the Thunderdome, this is also happening. During the dark and light, we're also augmenting that antibody to change it into one of the different classes. So we have a diverse and comprehensive antibody pool. How do we do this? Because we already did a good bit of genetic editing, when I was making the pro B cell and the pre B cell and all of that. Well, we have an enzyme that you should definitely know. Activation induced cytokine deaminase, the AID enzyme. So what this does is it initiates the break and recombinase in DNA that codes for your BCRs. So it's in and of effect targeted mutation, targeted DNA shuffling. So you get a new pattern that codes for the class of antibody that was signaled for. So like I said, referenced with that hyper IgM syndrome, if I need a certain antibody, well then I have maybe that CD40 signal come in, or I'll have a different kind of signal come in that says, hey, this is more of a mucosal issue. Give me a bunch of IgA. I need it bad in my respiratory tract. Or maybe it's a really heavy bacterial issue, and we need the best opsonizers on the planet. Give me a bunch of IgG. Whatever signals in the area are going to select for the antibody class that we need in serum. So let's see here. That doesn't really do me too much good. We'll keep going. I thought I had a picture with AID, but I don't. That's okay. I think we can picture. So it's just hitting the shuffle button, depending on the signals present. All right. Final product. We've talked about this a couple times already, even back in unit 1. We're going for a plasma cell. So now, after I've done all that replication, I've done all of that affinity maturation, I've done all the class switching I need. So now I'm done. Now I've ascended into, I've finished all of my schooling. Right now I'm in the workforce. That's the plasma cell. So it's no longer doing any replication. Its antibody is set. It's good to go. So that can either stay in the secondary lymphoid organ, or sometimes it can home back to the bone marrow and hang out. Regardless, we're making antibodies out the butt. 2,000 a second, millions per hour, and that's just one cell. So you can imagine the order of magnitude of antibodies floating around when we have a really robust immune response. Some are short-lived. It really just depends on the pathogen involved, and some can be really long-lived, like your tetanus shot. Again, I don't know the biochemistry here. I just know that tetanus is more protein-based, so that peptide binding groove also is really helpful for activating T cells as well. So you just have a robust immune response to tetanus. That's why you can go like a decade without needing another booster. Or we become memory B cells. These are those quiescent B cells that rapidly proliferate upon reactivation. Okay, so they're going to hang out in a lymph node, in the spleen, and hope to God that that pathogen wants to try you again. And again, this is really important to understand affinity maturation here. because now these antibodies have gone through all of the training, gone through all of it, and they are ready to rock and roll. So memory B cells are really, really efficient at dispatching antibodies that are going to get rid of that secondary infection. All right, last but not least, IgG is the only antibody that crosses the placenta. So from mom to baby. And this is usually occurring in the 3rd trimester. All right, so keep that in mind. But why IgG? Highest serum percentage, so just on the numbers game there. It's monomeric, so it's really easy for it to cross. It doesn't have to worry about, being twice or 5 times the size like IgA or IgM. And placental cells actually express receptors for them. So this is pretty cool. So the newborn is provided with some passive immunity. It's just hanging out, being a leech on mom's various systems, and the immune system is no different. It's getting some passive immunological knowledge despite, not being directly exposed to the world. And that's fine. We can cut the fetus some slack. It hasn't gotten to form a full immune system yet, right? Maybe the liver is doing most of that hematopoiesis, and then hopefully by that 3rd trimester, that bone marrow is starting to kick up. But we don't have a fully functioning immune system yet, so mom takes care of it for us. So this is why there's some maternal vaccinations suggested for mom, because that IgG profile is going to get transferred over to the fetus. So that's really cool, real good understanding of anatomy, of physiology, and of immunology. So really cool idea here, right? We, God forbid something horrible infects the fetus or infects the newborn, and if they are capable of having responses baked in, then hopefully that drops any incidence of mortality or infection following birth. Something super important to consider, of course, you've probably heard premature infants have a litany of issues associated with them because they lose that tail end of development. So be it respiratory, be it cardio, what have you, there's a bunch of problems that can arise, and to pile on the issues here is that this occurs in the 3rd trimester. So preemies also have a decreased IgG profile because they didn't get to have the whole piece of the pie while developing in mom. So these are much more prone to infection. So I have no experience in the neonatal ward or anything like that, but I would assume there is a highly, highly sterile environment to make sure that these kids are protected because they have less defense. Okay, so I don't need you to know all the fanciness here, but you just have receptors, and they are able to get transferred into the fetal circulation. So it's just really cool. But something kind of freaky to think about. What if those antibodies don't like the fetus? Yeah, kind of scary, because they might deem something's foreign in there. And that's the case with the hemolytic disease of the newborn. This is a little complicated, and I'm not going to require you to know the mechanism of action. It has to do with if the plus or minus in your blood. So like I'm B positive. If the mom is negative and she had a child that was positive, the first birth is not really much of a problem. But now if there's a second birth that is also a fetus with a positive blood type, positive just means you have something called Rh on your blood cells. Negative means you don't. But during birth, the mom probably got exposed to Rh the first time. So if she has another child with a positive blood type, well, the immune system might deem that as foreign, since the mom is negative and has never seen Rh before. So thus, her immune system would deem it as foreign. So this is a really crazy case where the second round of having a positive Rh child can lead to some really scary conditions. So that's just one way to understand. I think that's why I like bringing up different pathologies, because, albeit sort of morbid, but understanding how things go wrong can actually help you understand that physiology. You're like, well, how is that fetus under any duress whatsoever? It's kind of separate from things. Yes, it is, but not IgG. Not IgG. IgG can get through. So if you have an IgG against Rh, that's really, really bad. So just some food for thought. I don't need you to know that pathway, but just understanding the importance of IgG's capability of crossing the placenta gives the fetus defense and sometimes can be detrimental. So really cool stuff. So that's going to do it for me today, guys. I thank you very much for your continued attention and support. Bye-bye.